Let's talk about the Wien Displacement Law. Okay, just to review, there's this concept of blackbody radiation, right? These are electromagnetic waves emitted by all objects. How they're emitted is this concept. Any object that's made of matter that has thermal energy, the atoms are vibrating. Let's imagine you have an electron and it vibrates from here to here, back and forth between these two positions, right? As it vibrates back and forth, when it moves from here to here, the electric field that surrounds that collapses and goes away. Well, when it collapses, these electric fields contain energy. And so when they collapse, they create magnetic fields, which when they collapse, create electric fields, which create magnetic fields, et cetera, right? So if you take an electric charge and you accelerate it, you will get an electromagnetic wave. That's how you do it. Okay, this is how radio waves are transmitted. We just pump electrons back and forth in antennas, and we can generate electromagnetic waves, right? Now, this is a picture of the distribution. This is the intensity of blackbody radiation versus the wavelength. Notice that there's a lot of long wavelengths that are created. There's a lot of short ones, and there's this sort of this distribution. This is a Blackbody curve. This is what Max Planck was trying to figure out when he discovered quantum mechanics, basically, or it discovered him or something, right? And the reason for that is that, remember, when you look at a hot object, the molecules are not moving all the same speed. They all have different accelerations, so they broadcast different wavelengths, right? Okay. And if we look at this, thing, you'll notice that there's one that is the most probable. It's the most intense wavelength, right? And we call that guy Lambda Max, right? Okay. But blackbody radiation, back to blackbody radiation, right? It is basically, if you're standing at the bonfire at the homecoming dance, right? You can only stand so close to it before you just will burn up, right? Yet, if it's a cold night, you can see your breath. So the air is cold, but you feel hot, right? How is that possible, right? Well, it's possible because these photons, this electromagnetic radiation from that fire is traveling through the air, is not interacting with the air, not heating the air up, but it heats you up because you block it, right? Okay. Try this. Open up the refrigerator, and if you have an incandescent bulb in your refrigerator, some do, or freezer, right? Put your hand by the bulb. It'll feel warm. Then touch the bulb. The bulb will be cold, right? Well, your hand feels warm because of the radiation from that bulb, right? But the bulb feels cold because it's cold. That's conduction, right? Now, if you look at this curve here, you'll see that this is 6,000, that's 5,000, that's 4,000. These are cooler and cooler stars, probably, right? Okay. As the star gets cooler, the wavelength gets longer, right? As the star gets cooler, the wavelength gets smaller, or longer, sorry, wavelength gets longer, which means that it gets redder, okay? And as you go this way, right, the stars are getting hotter, right? 6,000 is here, right? And if you look at that peak, right, that's hotter, okay? So when you look up in the sky and you see a red star is cool. Why is it cool? Well, look at this. A star with a surface temperature of 4,000 kelvins has a big wavelength, right? It's even, in fact, its peak would be beyond red, right? It'd be infrared, but you'd see some of this red there, okay? When you look at our sun, it looks yellow, right? Because the peak is right at yellow, but it's got all this stuff, right? And then there are even hotter stars, right? That are like, whoa, got some peak here that's way, in the ultraviolet, right? Okay, so a red star is actually a cool star, and a blue star is actually a hot star, right? And then I just want to plant this idea too, right? Because there's a relationship between the temperature and the wavelength, right? If you're thinking about the Earth, right, the sun is about 6,000 kelvins, right? In fact, the reason that we can see, the reason that the visible spectrum is the visible spectrum is because we've evolved to see the light from the sun over billions of years or whatever, right? It's not a coincidence that we happen to see the light that is our sun predominantly makes, right? Okay, so here's the sun at roughly 6,000 kelvins, right? Whoops, 6,000. Add another zero to that, right? And it's broadcasting stuff that's in really, really short wavelengths, right? Like hundreds of nanometers, right? Down to the Earth. When it strikes the Earth, it warms the Earth up. It heats the Earth, the surface, right? And the surface of the Earth, this is say 6,000 kelvins. right? The surface of the Earth is maybe 300 kelvins roughly in rough terms, right? And so it's going to be broadcasting heat, its peak is going to be way down here, right? And so it's going to be broadcasting, these are infrared waves, okay? And it turns out that there are certain gases that block infrared, but they don't block this high frequency stuff, right? And those are the greenhouse gases. Okay, let's go and look at some examples here. Let's look at the Wien. Actually, I think I've got an example of a. Yeah, take a look at this. Notice that there's no frost under this tree, right? That's probably because the cold night sky is very, very cold. This happened on a cold night, right? And so the ground radiated this heat up into space, and there's nothing really. The atmosphere doesn't really absorb a lot of that, right? And so not much of it was broadcast back down. But the stuff that was radiated from the ground hit this tree, and the tree re-radiated it back. The tree kind of blocked that. And so this did not get as cold because it didn't see the cold night sky. This stuff did see the cold night sky. Just try that. If you sleep out and in a sleeping bag without a tent, it's much warmer to be under a tree than to be way out in the open, even if there's no wind or anything, right? Just try it. I know this from experience. All right. And then this is called the Wien Displacement Law. And this says that if you find the maximum wavelength, it's related to the temperature of the object with this simple equation. It's just inverse, right? So here is the maximum wavelength right there. We could figure this out, whatever that is, right? Right, here's this maximum. Here's this maximum. Right? Here's this maximum. Notice it's like, there's some relationship here, right? Okay. It's all related by this, okay? And they do this. This is sort of a strange thing. Most of us give this the units of meters Kelvin, okay? But let's just look at this. So what this means is that the bigger the T is, the smaller that wavelength is, right? So the hotter it is, the bluer the wavelength is. The smaller this is, the redder that wavelength is, right? Red is toward big wavelength and blue is towards small wavelength, right? Okay, let's do an example of this. All right, a star has a peak blackbody wavelength of 501 nanometers. So lambda max is 501 times 10 to the minus ninth meters, right? So nano means 10 to the minus ninth, right? Okay, so let's figure this out. What is its temperature? So the temperature is going to be 2.90 times 10 to the minus third meters Kelvin divided by 501 times 10 to the minus ninth meters. Let's do this. And that is 5788 kelvins, right? Or roughly 5790 kelvins. And this is the sun, right? This, by the way, is yellow light, right? 501 nanometers. We're talking about this spot right here. Okay, that's the peak right there. And they have it at 6,000 kelvins, which we approximately are at, right? All right, so let's look at the next example. What is the peak radiation of the surface of ocean water that's at 21 Celsius? Right, so let's figure this out. 21 Celsius. So the temperature is 273.15 plus 21 is 294.15. And now it's extremely important that you add that 0.15, and that's just like the most important thing here, right? Okay, did I do that right? I did. All right, so then, therefore, our lambda max is going to equal 2.90 times 10 to the minus third meter kelvins over 294.15. Okay, so that is 9.86 times 10 to the minus sixth meters, or 9.86 micrometers, right? Okay. And then the question is, what part of the electromagnetic spectrum is that? Well, let's take a look, shall we? There it is. Okay, that's roughly 10 micrometers, right? Which puts it like here. Right? It's below visible. It's in the near infrared, mid infrared. It's not far infrared though, because that would be too far. Okay. All right. I think that's all we need to say about that. But maybe there's something else I need to say. I don't know.